We have seen now the analogy of calculating the normal of a surface and then transformation of a surface. That comes to transpose and inverse of the transformation matrix. That if a surface is transformed by a matrix, if I calculate inverse and transpose of that matrix, then that comes to kind of the transformation for its norm. So if I am calculating, like I calculate light vector and I calculate spot direction, then I calculate I vector, means from I to, means there are so many vectors we calculate. Okay, but when we think about the surfaces, then we go with the normal transformation. When we see about like a spot angle is one of them, which is kind of, or a simple normal when we calculate, like when we go with the diffuse calculation, then light and simple normal, that L dot n. So simple normal, or if a surface is transforming, then how normal transform, or if light is source is transforming, then how it's a spot angle will transform. So both cannot be same, and it is transpose and inverse of the surface transformation matrix. What is surface transformation matrix? Okay. What is the story behind the curtain? So OpenGL is nothing but it's a game of matrices. Okay, so OpenGL stuff, they invented few matrices. Like if someone transforms, then it will transform. If someone transforms by 20 in x direction, okay, I have to transform in x direction 20. So this is the input. And another is transformation matrix for the transformation, passes through the media, and the new output is the transformed one. So what is this matrix? Transformation matrix for what is matrix for the transformation? What is it? What is it? Or if I do scaling, if I do rotation, if I go for orthographic projection, if I go for perspective projection, what matrix, the media in the, you can refer, please refer, matrix tutorial. So where input get kind of transformed, input get mixed with the kind of media and it changes. Then what is the media? So media is different from translation, rotation, scaling, perspective, orthographic projection and everything. So OpenGL is a game of vertices and OpenGL is a game of vertex transformation. So if I do transformation in translation, if I do transformation in rotation, and if I do transformation in the scaling, what happens? Okay. So if I see the inside story of the transformation, if the input goes and it do correlation with the or matrix multiplication with the transformation, separate media or separate transformation matrices, what happens? If we see little closely, then you will really understand the difference between surface and normal. What is a surface and what is a normal? If we understand the basic difference between surface and normal, then we can avoid transpose and inverse. Probably this is not possible anywhere. This discussion has never happened anywhere. So that we'll see that if we have transformation matrices, and then if I do transformation of a surface, means vertex on a surface, what it does, and if I do transformation on a normal, what it does. Why it creates problem when we go for transformation with normal matrix and we need transpose and inverse. If that problem, if we sort out, then we can reduce lots and lots of calculations. Means just think about a calculation. If we don't put this calculation transpose inverse, and then we have to put in shader, then we have to put in the code partition. Still, every movement of one, if I don't go for multiple color bubbles, single color bubble, and then for each movement of each item, it draws all the items. One item is set of VA. If my scene if my scene has 2000 items, just think that if one item moves 2000 draws, 2000 times transpose and inverse gets calculated. Okay, if I am not going VA over inverse per item, every point. Now, if in 1 second, if it moves 10 times one item, how many matrix multiplication we need to do in the CPU? If I place in GPU, we can place in GPU, okay, but it will happen per vertex and per fragment. That is another problem, okay, because GPU, that shaders get called per vertex in the, not per VAO, per vertex. So per vertex shader and per fragment shader. So we can't afford doing this kind of transpose inverse there. So we have to do in CPU only. And if we do CPU, each draw 1000 times we have to calculate transpose and inverse. Think about the expenditure. Okay. So if we go little in depth, can we save it? If we understand the different media, please refer to the matrix tutorial. We talk about the different vertices and then different kind of media and output and input and so many. Then we can really save lot of CPU time and it will be faster. Graphics is kind of, it makes sense when it happens, anything, if it happens in time. Otherwise, if I draw something and it takes more time than we expect or we have given to it, then what will happen? Nothing will happen. It will start dropping the frames. You will lose the information. So, why to lose information when it is not required? So, that we'll see. Okay, so we'll proceed on the surface normal and normal transformation. So we have we have seen that the surface and normal are two different things, and any vertex on surface is it's a vertex, whereas normal is a direction, so normal is a vector. Okay, so there is a vertex. This is a point on the surface, and this is a point, whereas normal is a direction. This is a point, it has coordinate, but normal has no coordinate, it's a direction. Okay, so if there is a kind of transformation on the vertex M, then normal transformation, the normal happens as inverse of the M and then it's transpose. So this is what we have seen. So this is the story right now. Okay, so now we'll move. Now, if this is the surface, then this is the normal. So surface, like generally, it has, we can say that, okay, so V is a point on the surface, but surface has area and minimum the set of vertices that form an area. So that is a triangle. Okay, so this is surface and this is normal. Okay, what we can do on the surface? So we can translate the surface. So surface is here and surface translated to here. So surface can be translated. Surface can be scaled. Now it has become smaller. Surface can be rotated. So surface can be translated. It can be rotated and it can be scaled. So three things on the surface is possible. I believe I can show it. There is nothing. Okay, so we can see surface and normal on the surface. So if surface is kind of now surface we are translating. Okay. So these are translations. Okay. Now I can scale the surface. Scale down. This is translation. Scaling. Scale down. Or I can rotate the surface. Okay, so this is the concept. Now, in kind of matrix tutorial, we have seen that if there is an input X and there is a media or matrix in between and it constitutes to Y as output, then we can say X multiplied by the matrix is Y, means X is passing through the media and this input if I multiply with M, then it becomes Y. Okay. So nice it is. So this is about this. Now what is X? So input is in form of X, Y, Z and W. This is the fourth parameter and typically we divide everything by W. Now if input is like this and W is 1, then there is a point. If W is 0, then certainly this point is on infinity because divided by. So this is the kind of concept of X. And then M, media is a matrix. So if X passes through media, it becomes Y. What is the media? Okay, so if we are translating, then it has to pass through this matrix. If we are rotating, like for example, so translating X, Y, Z is kind of fourth column. And if I rotating, so I have taken example of rotation around X axis. Then it has to pass through this matrix. If I am scaling, then it has to pass through this matrix. If I am doing GL frustum, means perspective projection, then it has to pass through this matrix. Okay? Can we see that it changes? Like if I just translate on the right side, can we see it a little bit? It is rotating. See? Even though I am just translating, so this is perspective projection. So the input, okay, the input is passing through the matrix. Okay, so when input passes through a matrix, it changes. So if it is translation, it has to pass through this matrix. If it is rotation along x-axis, it has to pass through this matrix, scaling or perspective. So if I have an input x, so x is like in kind of electronics, or so these areas, x is typically the input, the current level or voltage level, and media is a set of resistance through which it passes, or in communications like it may pass through some media like air or any media. Okay, so signal gets distorted, but here in OpenGL, x is nothing but a coordinate and media is nothing but matrix. So a coordinate, if passes through a matrix, it changes. What is the matrix depends upon what we want. Okay, so from translation to rotation to scale and then perspective projection. So that is the story. Okay, let's try. Means kind of I am translating. So if I am translating x, y and z, all three, and I have input as 0, 0, 0. So the point is kind of it is at origin. If it is at origin and I am translating x, y, z in three directions, then new point is x, y, z. Can we see? I mean it's simple multiplication. Okay, if two matrices are multiplied, it is x, y, z. So new point. So new point. So what I want to say is, okay, so if there is a coordinate like this, okay, so probably red is x-axis and green is y-axis and z is blue. Okay, and I have a point at the origin. Okay, if I translate it, okay, in x direction, y direction, z direction, this point now it would sit somewhere here as per the translation. How much it would shift? If there is a translation of x in x direction, y in y direction, z, so that is the new coordinate. We change the coordinate from origin to new origin. How it changed? It just multiplied by a matrix. That's it. Okay, now what about if there are two media? Input signal passes through a matrix and it becomes output signal. Output signal passes through a matrix and it becomes a new output. So this output becomes input to the second media, and this is the story. Two matrices. Input first multiplied by matrix 1, that become input to matrix 2, and that is the output. But in OpenGL, first we specify matrices and then we provide the actual drawing, like what is the vertices. So it is opposite way. If we specify in opposite way, it happens opposite way. So first input is multiplied by nearest matrix and then multiplied by M2. Okay, I mean I can see this. So whatever the program we wrote now here, so I'll do kind of some okay, so in display we are translating minus 15. So I think we have already, so before translation what is the model view matrix, and after the translation what is the model view matrix. So we'll see that. Okay, so before translation it is unit matrix, 1, 1 in the diagonal. Okay, and after the translation can we see minus 15, that is in the third row. This is the first row. Okay, so probably I can print it in different way. Before translation and after translation. Okay, so before translation and after translation. Okay, so far better. Now it is kind of a unity matrix. So whereas after the translation can we see X, Y and Z. So Z components minus 15 happened because I did translation of minus. Okay, so this is the story. Now I'll see the code. So when it enters, first thing we do is minus 15, like in this reshape. Whenever it reshaping, we are loading the model view, setting it identity. So it's identity matrix. And in the identity matrix, now we kind of we translating by minus 15. If I am translating by minus 15, everything is going in minus 15, means from the origin it is shifting minus 15 in the minus Z direction. Okay, so if I do kind of minus 55, okay, so it will start very small at the beginning only. Can we see? Okay, so see the size. So it went far. Okay, so it went far. Okay, so I can translate it in minus Z this much and X 20. So it automatically it will go right. Not okay, we can see it is at right. Small and light, right? Now we'll make it kind of left and big. So I will say left and it should be bigger. So only minus 5. Okay, I believe it is very big and it did not appear. So not that that big. Okay, so I'll make it kind of, or minus 20 it became too much. Okay, for big. So I'll say minus 2 and try. It should be on left side. Okay, so far better. So it is on left side and it is very big. So this is how it's happening because it is passing through translation matrix. Okay, so Now the item is at 0 origin and we are passing through the translation matrix. Okay, now story is if there are two matrices M1, M2. In OpenGL we specify M1, M1. So we specify matrices first and then drawing happens. So this is the input right side. It multiplies with matrix 1 and then multiplies with matrix 2. Okay, so what we can do is we can kind of rotate and then translate. Okay, so okay, this is how it is. So GL translate. Okay, so we rotate 30 degree along y axis. Okay, and then we translate -2. Let's see. I think GL translate will give it kind of -15, so it should be nicely visible. Okay, so it should be kind of translated. Can we see? At the beginning only it is translated. It is rotated. So first it is translated. First it is rotated and it is, so this is happening in kind of a grand coordinate. So please refer transformation tutorial. Okay. So there we talk about local and global or grand. So this is transformed through the global. Okay. So that is the story. So if I have a kind of, we can see what it printed. Okay, so before translation it was identity matrix. After translation, okay, this is -2x, -15, that is Z, and these are angular. Okay, rotation it made. So this is how it made. So we can see translation and rotation both inside the matrix. Okay, so if there is a drawing and there is an input, there is a media, first it kind of do the matrix multiplication and then do matrix multiplication. If we through local coordinate system, then there is another way from looking from left to right. But actual matrix multiplication happens from right to left because the input is on the right, output is on the left. So it starts from the right and proceed toward the left. Okay, so if I am rotating along y-axis, so let's rotate along x-axis the way we have. So we'll rotate along x-axis 30 degree and we'll see the matrix. Now matrix we can see like anyway -2 and -15 is x and z, and this is cos 30 minus sin 30, sin 30, cos 30. Okay, this is what it is. Cos 30 minus sin 30, cos 30, sin 30. Okay, so this is what we are seeing these two. And this is x translation, y translation. So, okay, so it's a play of matrix, nothing more than that. So now we are kind of multiplying by rotation and translation. Okay, so as per the formula, x is multiplied by matrix 1 and then matrix 2. So if x is 0, 0, 0 and 1, it is multiplied by a matrix, rotation matrix, whatever comes, then it is multiplied by GL trans. So this is the story. Okay, so what we can see now is if I have a coordinate 0, 0, 1. So there is one example, like if I have a coordinate if I have a coordinate 0, 0, 1 and 1 dot 0. So z is 1, x, y is 0. And if I transform, okay, translate x, y, z, then it will be x, y and 1 plus z. So z is kind of changing. If I am in the input, the vertex is 0, 0, 1, z is 1, others are 0. Transformation, the translation happens only in z. This is what we are seeing. Okay, now kind of let's see the rotation. Now same 0, 0, 1. So point is 0, 0, 1. Okay. If that is the case, then if I rotate along x-axis 30 degree, then it becomes 0. Okay. So this is the along x-axis A angle. So that will become 0 minus sine A cos A 1 dot 0. It's a simple matrix multiplication. If I translate a point 0, 0, 1, it will become like this. If I rotate 0, 0, 1, it will become like this. Okay, so I think we can just keep our breath. Okay, now we talked about two media and two media in OpenGL. Now, can we remember? If there is a transformation of M in a vertex position, then there is a transformation of M minus 1 inverse and then transpose in the normal. So if I do transformation of M in the surface, then normal get transformed by inverse and transpose of the transformation that happens in the surface. Okay, now we see the transformation of the vertex. We gave example that if vertex is like this, like 1, then how it will transform if it is translation, and how it will transform it is rotation, if it is rotation. Okay, so if input is 0, 0, 1, what will be the output if it is rotated? If input is 0, 0, 1, what will be the output if it is translated? Okay, now this is the vertex transformation we saw, and net transformation follows this rule. Okay, input is multiplied by the last. So if I take our code example, then input will be multiplied, first this matrix, rotation matrix would be multiplied, then translation. We are doing translation first, then rotation, then we are drawing it. Okay, so this is rotation matrix and this is translation matrix. So, okay, so we saw that this is how it happens. First rotation get multiplied and then translation. Anyway, now let's move kind of how the normal would get transformation. Okay, now I have input of 0, 0, 1. Okay, how normal would get transformation? So this is in normal. Okay, so this is the vertex point, and now if I want like, okay, so if this is the kind of a point on the surface 0, 0, 1, and this is the matrix we are doing the transformation, means what I want to say is, if I am doing transformation of M in V, then there is a transformation of inverse and transpose in the normal. Okay, if that is true, then this is M and this is V. Now we have to find transpose and inverse of this. Okay, so inverse of this is this, and if we do the transpose, then this will come here. Okay, so transpose of the translation is like this. Okay, now if I do the calculation, okay, can we see it is unchanged? 0, 0, 1. 1 is the fourth coordinate. There is change only in the fourth coordinate. Can we see? If I am doing transformation, plane transformation, then there is a change in z coordinate, 1 plus z, and x and y also got introduced. So 0, 0, 1 got translated by x, y and z. Can we see this very clearly? New point is it has x field, y field, z modified, z also got added. But if I do transpose and inverse of the matrix, and same thing, so first we calculated the inverse, then transpose, okay, and now transpose inverse, if I multiply with the same point, there is no change. Can we see? There is no change at all. It remains unaffected. Only the fourth parameter, so that we can divide. I mean, if I normalize it is pretty well, it is same. Okay, let's do transpose and inverse for the rotation. So, okay, I mean, we have not done transpose and inverse of the rotation. Okay, anyway, just leave it. Okay, now we have done transpose and inverse of the translation and we see that nothing changes. Now, I have a matrix, I have a kind of two media. One is translation, one is rotation. Now, all together we will calculate inverse, transpose. After calculating this, then we will multiply this with the input and we will see the output. Okay. Okay, so this is not what we want. So there is no output here, or output should not be considered. Okay, so probably I can modify this slide. Okay, so what we are trying to find is, I think we can just leave right side for right now, or we can just modify. There's no harm. Okay. Okay, so we are calculating this, and that will find the output. Okay, now I have two matrices. One is rotation and one is translation, and we have already calculated this. If it is only translation, if it is only rotation, okay, or we have also calculated if it is kind of rotation and translation. Okay, now we will do the we'll calculate the net matrix in the for the normal, so that will be inverse and transpose whatever we get. So this is okay, so this will calculate the okay. Now I think font is pretty small, so we'll do these multiplication. Okay, so this and this, whatever we receive, okay, then we'll do inverse, and then we will do transpose. Okay, so I should have removed this line also. So we'll just calculate the transpose and inverse of the matrix. Okay, so then we will probably we will multiply with the input. Okay, so what we are trying to do is M1 and M2. Okay, so this we will multiply and we will calculate the transpose and inverse, and we'll see that what is the effective matrix. Okay, so what we are trying to do, so this we can also write, probably we can, okay, so okay, so okay, what we are trying to, so we can just have it, and what we are trying to find is okay. Okay, so now I have two matrices, M1 and M2. Okay, so M1 and M2, they constitute a matrix. We are trying to get the transpose and inverse of M1 and M2. So if input is transformed by M1 into M2, then how much the normal would get transformed? That is nothing but transpose and inverse of these two multiplication. Okay, so by now we have seen this much detail where we did the transpose and inverse of a translation, and now we are doing the transpose and inverse of two matrices, translation and rotation. and we'll see the effect on the input of the transpose and inverse. Now we'll multiply with these two. If I multiply, it becomes matrix like this. So now I have to find inverse and transpose. Okay, so what is the inverse of a matrix? That is adjugate of a matrix divided by its kind of magnitude. Okay, that is the inverse. So this is kind of called cofactor. So cofactor of the matrix we have written this big. If this is the matrix, this matrix we have received after multiplying translation and rotation. If there is a translation and rotation on the surface, how much translation and rotation would happen in the normal? Okay, that is the calculation. For that, we are calculating transpose and inverse. So first we multiply these two, and if we multiply these two, it comes to this stage. And if I want to inverse it, then I have to calculate the cofactor of each entity, this big. Okay, so if I get the cofactor of this entity, okay, then I have to do the transpose. Now I have taken x equal to 0 and y equal to 0, z equal to 1. This is what we want. Okay, so we are calculating for x0, y0 and z. So this one we saw that if I do the normal translation, then this is the kind of new vertex. If input is 0, 0, 1, the new is x, y, 1 plus z. If I do kind of transpose and inverse, and if I do multiplication, then modification only happens in the W. Whereas in the surface, okay, modification happens everywhere, but in the normal, modification happens only in the W. What about this? Okay, so it leads to this matrix, and now we have to calculate T, but we want only for x0, y0 and z equal to 0. So if I here, now I'll if I move ahead and then I calculate it. So what we are doing here, if this is the kind of cofactors, so this is one matrix, this is one matrix, these are cofactor of the bigger matrices. Now I have to calculate the determinant. So if I want determinant, then I have to keep this and multiply these diagonals. Then I have to keep this, multiply then whatever the determinant comes. So like that for every matrix we have to do, and we did. For every matrix we did, keeping x equal to 0, y equal to 0 and z equal to 1. So it comes to cos square a plus sin square a, and then like this, and then cos square a and sin square a. So this much we got. Now we have to calculate transpose, then again transpose. So inverse is, I have to find cofactors, and once we calculate the cofactor, I have to do the transpose. Okay, so net if I see the transpose and inverse of the matrix, then whatever we have received after calculating the cofactor, that is the adjugate matrix, I am not calculating the magnitude. Okay, so if this is the magnitude A by magnitude, so I am not calculating the magnitude. So two transpose. One transpose anyway comes in the inverse, again transpose. So they cancel each other, and we get this as kind of transpose and inverse of this matrix. If I have a translation matrix and rotation matrix, and I want to calculate the transformation in the normal, then I have to calculate transpose and inverse. So if I calculate the transpose and inverse of this matrix, it results in this. So cos square a plus sin square a is 1. Cos square a plus sin square a is 1. And then others. So this is the net matrix I am getting after transpose and inverse. Okay. So if I see here, for the simple translation, if I do transpose and inverse, I get this as net matrix. If this is the matrix, then this is the net matrix. Then first with the original matrix I multiply the vertex, I get new vertex. But after doing the transpose and inverse, if I multiply the vertex, okay, then I get, if I multiply the normal, this is normal. Normal is unchanged, only W changes in the translation. But if translation and rotation both are there, then this is the new matrix. Okay. Against these two, if translation and rotation are two matrices, their transpose and inverse comes to this matrix. This is a matrix. Okay. Can we see a kind of have we seen this matrix around? Nowhere. Okay, so we have not seen this matrix anywhere. So very fine. Let's go for multiplication. So if this is the matrix, okay, and I multiply this with the if I have a normal like 0, 0, 1 and z, this is what we are seeing. This is what we are doing. Okay. So I have a point 0, 0, 1, 1.0. So now we will do the computation. Okay, so now time has come that if this is the matrix, if this is the matrix, if this is the new transpose and inverse matrix, now we have to kind of do and the new points are, the input points are 0, 0, 1 and 1, okay, 1.0. Okay, now if I multiply, okay, so this with that, so this can be represented like this. This is input. Okay, now can we see that it would become, so we will do the computation. Okay, so first row of the matrix and first column, if we multiply, then it will become 0. Next, if I multiply, then it will become minus sin A. Next, if we multiply, then it will become cos A. Okay, if I am right. Next, if I multiply, then it would become minus cos A plus 1. Okay, so this is what we are getting, 0 and minus sin A. Okay, then minus cos A. Okay, cos A, then minus cos A plus 1. So this is what we are getting after doing the okay. Now if I take x, y, z, 0 minus sine A cos A, okay, W we leave it. Now can we remember something? If there is a rotation, okay, then minus sine A cos A, this is the way it modifies. Minus sine A cos A, minus sine A cos A. And if we see the matrix, it is exactly same if I leave the fourth row. Okay. So fourth row, if I exclude, then top three rows are same. And that's why we are getting same thing. Can we see? Okay, so in the matrix, top three rows are same. Fourth row is different. This is the translation row. Now, if I have two matrices, translate matrix and rotation matrix, and if I do transpose and inverse of these two matrix multiplication, it comes to a matrix where there is only rotation. That what we do, the translation, it comes as fourth row, which has no weightage. It just compute in the W. Otherwise, it is only angular. Can we see this? This proves that transpose and inverse, it is affected only by rotation, not by the translation. That's why we do transpose and inverse. Okay, if there is a vertex and there is a transformation M, then in the normal there is a transformation inverse and transpose. What is inverse and transpose? Inverse and transpose is nothing but only rotation. There is no translation. Can we see this? If I translate, normal doesn't change. Normal is a direction. If I scale, normal doesn't change. But if I rotate, normal changes. That's the difference between the kind of surface transformation and normal transformation. Surface transformation changes with translation, it changes with scaling, okay? It changes with rotation, but normal doesn't change with the translation and scaling. It changes only if I rotate. Okay. Now I can't afford transforming normal. If I am transforming a vertex by M matrix, I cannot afford transforming normal also by M matrix. If I do so, can we see in the calculation? Okay. So, in the calculation, if I have a vertex 0, 0, 1 and there is a transformation matrix, then can we see if I do simple multiplication, it fills x, y, z. Means normal direction is changing if I do the translation that I don't want. Normal direction must change. Okay. So, if I comment this, and I execute this code, okay, normal is changing. If I do translation, normal is not changing. Can we see? It is same. If I scale it, it is not changing. Normal direction is same. But if I rotate, normal is changing. That's the difference between point on the surface and point on the normal. Normal must be modified only when there is a rotation on the surface. Otherwise, it should not be modified at all. Okay, so that is the scenario. Now, what I'm trying to prove now is, okay, very nice. Now I have calculation wherever I want to do the rotation on the normal. I have to calculate transpose and inverse. Blindly we cannot do anything, but not required. Transpose and inverse only brings the rotation part. Okay, so can we say like this? If there is a model view matrix, if there is a matrix M, inverse and then transpose, if I take out the matrix part, okay, so its matrix part, matrix 3 means top 3 row and top 3 column, and its rotation part top 3 row and top 3 column, they are same. Okay, and now if I see the matrices, the beginning translation changes fourth column. If I do transpose, inverse and transpose, this fourth column becomes here in the fourth row. First 3 row and first 3 column, they are only for rotation and they never change. Okay, anywhere, see. So first row, 3 row and 3 column are unaffected by translation. They are modified only kind of if we do the rotation. Okay, if that is true, okay, if that is true, then whatever the transformation we do on M, same transformation we can do on normal. If I take out only the first 3 row and column. Okay, so if like in the OpenGL shaders code, okay, like I'll show my kind of shader software code. Okay, generally what we do, we calculate transpose inverse of the model, and whenever we have to do transformation in the normal, we go with the transpose and inverse. Transpose and inverse are calculated as transpose and inverse of the model view matrix that is passed to the transpose inverse view. This much calculation we don't need. Okay, if I have plain model view space, plain model view like there are 3 things: coordinate, normal and texture coordinate. So coordinate get transformed by model view matrix, whereas normal get transformed by transpose inverse of the model view. We don't need. We can save lot of CPU computation. What do? We just take out the matrix top 3 row and column of the model view sphere to calculate the transformation in the normal. Okay, so normal, the transformation what we receive in the normal is nothing but only rotation. That is the kind of top 3 row and top 3 column of the model view matrix. We don't need. Okay, so we don't need any calculation of transpose inverse at all. In lighting also we don't need. In lighting also we are just passing the simple model view. Okay, can we see? Means if I am doing the spot direction, only first 3 we are passing. Okay, so like a spot direction is a direction. Spot direction is like a normal, it has direction. Only first 3 we are passing. If I see the fragment shader, we are not doing any calculation at all. Okay, there is no kind of there is nothing as model view lighting and transpose inverse of lighting, nothing. There is no transpose inverse at all in the shader code, not required. This saves a lot. This kind of do the high speed kind of graphics. Okay, probably this cannot be found in any book. Means anyone can understand. Means this is local. This is not international. Okay, so this can be kind of we can achieve, like if I am doing any transpose and inverse, we land up in the same top 3 row and column what we see in the rotation. Okay, if we are doing a rotation transformation in the M, if vertex is transformed by M, we can take out top 3 row and column, and that's it, not required to calculate transpose and inverse. That is the normal transpose. This computation is not required. Means this research, what has been done by people this much, whatever we saw in the training, all are useless, not required. See how much we did calculating the transpose, and this much research we did from the first slide. How to calculate normal, and then this and that, and then we moved ahead, and then finally we came to conclusion that if a vertex is transformed by M matrix, then normal must be transformed by transpose inverse and transpose, not required. If a vertex is transformed by a matrix M, then we can just take the top 3, okay, and that is the transformation on the normal. This much mathematics is not required. This is what we find in all internet and all the 3D books. Okay, so people, they just mug up. Okay, so this much model view, and the shader code what we see, it is completely kind of untd with transpose and inverse here and there, calculating, and in the lighting calculation transpose and inverse in the then we have to specify from the Python code transpose. Means people that do, they die in this kind of nonsense, not required this much. Many research are not required. Okay, so conclusion is whatever we have done this much to show, not required. Okay, so if I do transpose and inverse and transpose to find the kind of transformation in the normal, not required. Whatever transformation we are doing on the vertex, just we have to take out the top 3. That's it. This is what we are doing in our vertex shader. Can we see this? Mat 3. Whatever model view transformation we are receiving for the vertex, like vertex is transformed by model view, same we are doing, just we take out the top 3. And for the kind of a spot direction, okay, in the Python code, spot direction in the Python code, whatever we do, we transpose anyway we do, because OpenGL stores in different way. We just take out the first 3 and first 3 columns. Okay, earlier we were also doing a transpose and transpose and then inverse. Okay, and in the kind of model view sphere also. Transpose and inverse, not required. Okay, so okay, so that is the concept. Anyway, with the new whatever the new algorithm is, means a kind of I can move ahead to publish this. So with the new algorithm, we have done all the solar system videos. So whatever we are kind of published in the solar system, moon rotation and whatever we have done, all are through kind of new calculation, not the traditional one. Okay, so I have another one. Okay, so this is lighting model, and where we are not calculating transforming normal by transpose and inverse, the way it is mentioned everywhere. Okay, in books also you will find why transpose and inverse to the normal is required. We have not done any transpose and inverse. Okay. Okay, I believe it should be visible. Now there is a road and kind of two cars are there and tree is there. Okay, so first car, if I turn it, can we see the lighting effect? It is perfect. And second car, if I rotate, then lighting on the tree are minimized. There is one default light that we have placed so that road can be seen. Okay. Now if it rotates, it's a spotlight. Now it is illuminating the road also. Okay. Same way, more light on the trees. Perfect. Car is moving on the highway. Okay, they are getting each other front light. Can we see their face is completely lightened? I mean, I can show like this. We can rotate complete thing and we can see each other's face. Okay, so probably I can scale it down. Okay, now I can show each other face. They are lightened. Can we see? This face is lightened and anyway other face is lightened that we saw. Now, first car is moving and can we see the headlight of the second car is not on the first car. Okay, I mean, I can make it bigger. Okay. Now first car is moving silently. If it happens to rotate, can we see the light it is throwing? All calculations are happening without transpose and inverse. Okay, I can rotate the first one also. Perfect. Okay, we can see the lighting on the trees. They are not perfect. It is better in one tree. It is better in both trees. Okay, so but it is required that we take out the top. It is kind of as a lab exercise that if I don't take out if I don't do the transpose inverse, then what we get? Okay, so if I don't do the transpose and inverse. Okay, so if I don't take out the top 3 rows and if I don't do the transpose inverse also, then in the normal, if I do the simple matrix multiplication, it will fill up x, y, z. Okay, and it would not show the kind of, it will go away immediately. I mean, there won't be any lighting at all. Okay, so replacement of transpose and inverse, okay, so is kind of matrix 3. If I take out the matrix 3, top 3 and column, it is done. Okay, so this slide is like generally we find in the book also, if input is x, y, z, w, then these model view projection, deep perspective and viewport transformation. So these are nothing but kind of media, and we have to multiply all this, and then we can kind of multiply with the x, y, z the way we did with the multiple media. So in the kind of transformation pipelining, so it also follows the set of vertices, and once it is multiplied with the input, then it results in kind of the output. Okay, so since beginning we saw how to find the normal. So a surface is there and there is a norm, normal is a vector has a direction, and we saw the kind of two things, one is analytical surface, one is polygon data. Any analytical surface we can find normal, one for the explicit surface definition, implicit surface definition. In the explicit we get the kind of tangents and then we make it cross and we get the normal. Okay, and in the implicit we get the formula in x, y, z, and then we calculate the gradient. Okay, and that we saw in the implicit. Okay, in the polygon data we saw that if we have points, we have a surface, then normal along the full surface. Polygon data is nothing but it's a kind of set of facets. Each facet has same normal, and we have to find two lines, and then we get the cross to get the normal. Okay, and now we saw that how we can kind of make it smoother, like for each vertices we calculate the average or weighted average to get, like, instead of this we get a smooth. Then we went ahead to calculate if we transform a point on the surface, then how much normal would be transformed. But later we see that this transformation is not required if it is translation and scaling, but it is only required if it is rotation only. Okay, if that is the case, then transpose and inverse we calculated. Transpose and inverse to calculate the normal, and we found that first 3 row and column is nothing but the rotation only. See, cos A minus sin A cos A. We started with cos A minus sin A, cos A, sin A. It end up in the same thing. Cos A sin minus sin A, cos A sin. Only 4th row is different. It makes different if this row becomes column. The way we saw here, if there is a column of x, y, z, then it fills up. But if this column is transformed into row, 4th row, it doesn't affect it. That's why we do transpose and inverse. Okay, so that is not required. If I take top 3, okay, and then we do the math. Okay, so that's it.